Good afternoon. I just want to, for those of you who are feeling fatigued after our rather exciting morning, I just want to point out that this day is exceptional in our schedule in that we actually have 3 lectures. For the most part, there will be 2 lectures in the entire day, and we will have tutorials in the afternoon. Maybe the tutorials will be tiring in a different fashion, but at least you won't have to sit still. The first tutorial will be tomorrow, and I think that's the one that Gabi was referring to this morning. And after my talk and after the coffee, when we come back, one of the things we'll be talking about is preparations for not just that tutorial, but the other tutorials, including things that you may need to be downloading to your various laptops, software, in preparation for that. So something that we neglected to mention this morning, or to even tell you about, is that for those of you who have laptops, and I expect that's virtually everybody, during the tutorials you'll need to be using them, so you'll need to be bringing them in during the day. Okay, my task is a little bit different from Gabi's this morning, whereas she had a particular body of information that she wanted to talk to you about. I have a much more general charge here. We have a series of lectures on earth materials over the course of the week. I'll show you the schedule in a couple of slides. And each of the others are focused on one fairly specific topic or the other. And my task really is to give an overview of earth materials and to introduce a number of topics. And actually, a lot of the topics that I'm going to talk about are really simple. And when it seems too simple, I'm going to just substitute opinions instead of facts to try to keep it lively. Okay, so earth materials in some ways sits in the center of everything that we're doing, right? No matter where you are in this continuum, the geodynamicists have things that they need to know about material properties, whether that be density or viscosity and so forth, in order to do convection calculations or any sort of dynamic calculation. Similarly, the geochemists use information that comes from earth material studies, whether they be experiments or theoretical studies about phase equilibria. I could have put that on here, and in fact I should have, but element partitioning, isotope fractionation, melting, and so on. And also the seismologists depend on various earth materials measurements, elasticity, and so on, in order to convert their seismic velocities to some other kind of information that we may care about for the Earth, composition, temperature, and so on. So in this sense, earth materials is central. It also means that there's a bunch of us sitting in a room like this who maybe know next to nothing about seismology, but I think all of us know a little bit about earth materials because it touches on all of these things. And you may be wondering about this. A lot of this talk was made late at night. And I found myself making the introductory slides, and they all had arrows going every which way. So I just added some extras. Okay. So here I am today. The schedule will continue throughout this week and next week. Dave Ruby has expressed interest in giving his experimental studies lecture this Wednesday, and then his more topical talk on Monday. That's the opposite of what's in the schedule. And for the most part, the talks, except for I think Dave's Monday talk, really take a perspective on earth materials or a piece of real estate, the mantle or the core, and give a very specific perspective, whereas, or very specific body of information, I guess is what I mean. Whereas Dave's is something of a hybrid between, Dave's second lecture is something of a hybrid between an earth materials lecture and a topical lecture about the early Earth from the perspective of someone who is a material scientist or a mineral physicist. Also, I want to point out that one of our tutorials, the molecular dynamics tutorial that happens next week, is linked to one of the research talks. I think this is the only one that is this way. That is to say that Razvan Karakas, I think on Monday afternoon, is giving a brief 30-minute research talk that really is a prelude to the tutorial that he'll be leading on Wednesday. So make sure to see his research talk in preparation for this. Mm-hmm. The significance of the colors, I'll tell you right now, is that I'm colorblind.
Yeah, you gave the wrong answer.
Okay, so Earth materials or studies of mineral physics have various different approaches. There's, of course, observations. When absolutely forced to, we will look at rocks, but we will usually avoid it at all costs. If we do look at rocks, we'll try to turn it into something like spectroscopy, which is what this is here, which can be actually extremely interesting and useful. What this happens to be, it's rather small, is an infrared spectrum of the hydroxyl absorption of olivine. The way that we know that water, so-called water, is so important in the mantle is in part because of observations of natural materials which show that hydroxyl is a universal contaminant in natural mantle materials. And this has, as we'll sort of cover in a little bit, very important consequences for physical properties, melting, and so on. But it starts with an actual observations of rocks. I would say that most mineral physicists and people studying earth materials are engaged in some kinds of experiments, and experiments are a huge, probably the largest source of the constraints that we have within mineral physics, but also extending over to all the other associated fields. I'm not going to say much more about that because that's the subject of Dave's lecture in a couple of days. And then increasingly, there is a branch of mineral physics and earth material studies that makes reference to theory. This happens to be a simulation of I guess it's a silicate melt of the atomic positions in the silicate melt. And in fact, theory is getting more and more powerful, and we're finding more and more reasons to refer to theory when we have earth materials problems. So there's more of us doing it, and it's probably more important if you're not a mineral physicist to be aware of what the field is, and also what it can do, and I suppose what it can't do. So I wanted to digress a little bit about that, about earth materials theory. If you're not making observations and you're not doing experiments, then you must be doing something else, and you'll just call that theory, right? It's what we do when we work with calculations in the absence of observations. And there's a lot of different kinds of theory, some of which is relatively simple and has existed for more than a century, and some of which is cutting edge and has only been enabled recently by the advent of very fast computers. There's a certain, I put a continuum here. I could have put sort of a snob continuum as well, which is to say that, for people on this side, and I should say that if I do any of this, it's the stuff on the left here. It may seem very simple and very applied and empirically based. And as we move to the right, and I'll describe some more of this in greater detail in a moment, we get more and more first principles and more fewer empirical constraints are required. But considering that we're in an institute for theoretical physics, I think the theoretical physicists would consider even this to be fairly applied compared to some of the things that they're doing. But as we move to the right, we have the ability to use physics to make calculations that are not amenable to experiment, and that allow us to explore things that, first of all, are not within the realm of experiments, but also give us information not just about macroscopic properties, but the relationship between macroscopic properties and microscopic arrangements, the actual bonding and positions and motions of atoms. And in that sense, it's extremely powerful and extremely useful. Somewhere in between this pure theory, which is using various different elaborations of quantum mechanics, we have molecular dynamics. Molecular dynamics is calculating the properties or the structure of materials from the atoms using some assumptions about the forces between the atoms. And if it's classical molecular dynamics rather than using quantum mechanics, the forces that are assumed are classical Newtonian forces of various kinds. They give us information about again, the relationship between microscopic arrangements and physical properties, whether that be whether that be melting or diffusivity or what have you. They have this sort of classical molecular dynamics has the advantage that it's computationally relatively inexpensive compared to more pure theory. And as a consequence, one can use much larger ensembles of atoms. One can deal with atoms that are actually complex to calculate because they have many electrons, like iron and so forth. That's possible here, but it's much more computationally intensive. One can do calculations that amount to actually nanoseconds, whereas these amount to picoseconds, and so on. So depending on the problem that one is using, one may want to go over to the right and be using as few empirical constraints as possible because one is in a realm where the empirical constraints aren't very useful, or one may want to be over on the left where basically one is building up a whole bunch of different observations, whether they be measurements of diffusion coefficients or measurements of thermodynamic properties of enthalpy and heat capacity and equations of state and so forth. One of the advantages of the classical approaches is that you can build it into other codes fairly easily because it is not computationally expensive. One can do a geodynamics code where one has however many voxels of grid points, and in each voxel make a calculation, whether it be a diffusion calculation or a phase equilibria calculation, using these kinds of approaches. That really probably wouldn't be possible or even possible to contemplate for the more sophisticated kinds of calculations. Okay. What sort of things do we care about? I've divided, this is probably not a comprehensive list, but I've divided the different kinds of material properties we care about between equilibrium and non-equilibrium properties. I freely admit that, in fact, there's probably no such thing as equilibrium on the Earth. If there were, it would be kind of a dull place. There may be local equilibrium in certain places, but certainly not over large length scales or time scales. But phase equilibria, phase transitions, density and equations of state, element partitioning, solubility of one type of material into another, like solubility of a vapor into a magma, or solubility of trace elements into, say, core-forming material. Melting, which I guess is a subcategory of phase equilibria, and so on. Non-equilibrium, diffusion rheology, conductivities, grain growth and textures. Grain growth and textures is actually sort of the complex frontier of materials because it combines studies of microscopic properties with sort of mesoscale things. And I'll talk a little bit more about that. Don't tell me that lunch made you forget how to interrupt. Okay, so we care about a whole bunch of different variable space when we're talking about material properties, and the obvious ones are temperature and pressure. And you see, I told you arrows can go anywhere, right? Well, actually, it's deliberate that this one is a different color. Please tell me, are all of these the same except for this one? Yes. Okay, that's what I wanted. You'll see why in a moment. Composition is one arrow here, but of course composition is as many arrows as you care to contemplate. If you're a geochemist, it's 92, I suppose. Or if you're a xenologist, even more. So there's the different sorts of variables, but also, particularly when we're talking about non-equilibrium things like diffusion or grain growth or rheology and so forth, we care about times and rates, and we care about spatial scales. Textures is here in a different color because textures may or may not be an independent variable. Textures may actually be, in some circumstances, a product of all these other things, or depending on the problem that you're interested in, it may be a given and it may determine something like grain size or something like preferred orientation, anisotropy of grains and so forth. So textures is a different color because it's not necessarily an independent variable like all of the others, but sometimes it is. Okay, when it comes to deep earth materials, we get to expand our brains a little bit and think about conditions and materials in realms that aren't typical even for people who are used to squeezing things really, really hard. So I think this is sort of self-explanatory. The kinds of pressures and temperatures that existed during certain early Earth processes are far beyond things that we've ever seen since and hope ever to see. This is the same event from a different perspective, and I think Dave is probably going to show this Where's Dave? You're probably going to show this? You're not? Okay. Well, you have to. It's so artful. But this is to show that during a giant impact, a number of things that can happen that put materials under extreme conditions, and that may include processes such as fragmentation of planetary bodies or emulsification of planetary bodies, and understanding the physical properties associated with that are fairly interesting. And also, this stuff here is melt. So obviously we're talking about magma oceans, which we don't normally think about when we restrict ourselves to the last 4.4 billion years. And as a consequence, again, conditions that are more extreme than normal. And here we have a magma ocean, or a cartoon of one. It's the same cartoon that Dave showed this morning. And one of the interesting things about a magma ocean is that, in fact, the temperatures are very extreme. So if we have a completely molten mantle at some period of time, then we have an isentrope that looks like this. I guess Dave was saying that it wouldn't even look like this because there'd be extra entropy in the shallow region, and we'd be even hotter here. But that would make the point even stronger, that this is very quickly getting into realms where experiments are just really, really hard. When you're talking about 3,000, 4,000 kelvins, you're either talking about a really tiny laser spot in a diamond anvil, or pretty quickly, if you want to do a lot of things that you can't do in a diamond anvil, then you're doing it with calculations. You're doing it with theory instead.
Just to comment on that one, last Stickroot showed, and it's supported by shock experiments at Caltech, the liquid isentrope near the bottom of the mantle is actually steeper than the solidus or the liquidus, and that's important.
Yeah, one simple way to think about that, this here is the liquidus and the solidus of peridotite. And if you think about this isentrope just happens to be completely molten throughout the entire mantle. But if you cool it a little bit, it begins to crystallize in the middle, right? The first crystals to form are in the mid-mantle, and you have a magma ocean above, as we've always thought, but also a magma ocean below, right? So that's... There's also something else that's since Dave brought it up, there's something else that's very interesting about this isentrope here is a partially molten mantle. And so it's a mantle that's only completely molten to, from this angle I can't really tell, but maybe about 30 GPa or something like that. But look what it does through the rest of the mantle. It's in the partially molten state through about 100 GPa or through most of the mantle. So the way that magma oceans cool and the way that crystals and entropy are distributed within them, it's actually fairly intricate. Okay, continuing on the theme of extremes, this was also referred to earlier. In the aftermath of a giant impact, we may actually vaporize a significant portion of the planet. So we're dealing with rock vapor on the order of many thousands of kelvins at fairly low pressure. But even after that rock vapor goes away, what's left behind are these giant atmospheres of CO2 and water. So here's Venus with 90 bars of CO2 pressure today. That may be a fairly good analog for the kinds of conditions that existed early in the history of the planet. So if we talk about volatiles, if we talk about boundary conditions and insulation of the planet from radiative cooling and so forth, we have, again, extreme conditions. And extreme compositions. This is the last of my extremes. We're used to thinking about the mantle as the mantle is a certain composition. You may think it varies a little bit, but it's Forsterite 90, 90% magnesium, 10% iron by atomic proportions. Doesn't vary very much, but in fact, the building blocks of our planet include materials that are potentially quite different. And a great example is enstatite chondrites. And it doesn't have to be that enstatite chondrites are an important part of our planet or even necessarily a minority of the building blocks of a planet. They represent conditions of very low oxygen fugacity that may have prevailed during the early portion of the accretion of the planet. And under such conditions, the materials and the material properties might be really quite different. There's so little oxygen in an enstatite chondrite that there's basically no iron oxide, right? Virtually all of the iron is metallic iron. And then a number of the other elements that you normally think of as being lithophile and bonded up in silicates or oxides, like calcium and magnesium, are actually in part forming sulfides. Ninningerite here, or oldamite, that thing over there, calcium sulfide, magnesium sulfide. So we may need to consider a range of minerals or components in melts, if you will, and behavior in melts that's really quite different from normal.
Is somebody at some point going to talk about how much enstatite chondrite you could put into the earth? I know some people have said you can't have very much, but that material is of great interest because isotopically it has some similarity to the earth.
Bill?
I'm going to address some of that.
Good.
And I think also in Dave's lecture, he's not going to talk about enstatite chondrites per se, but I think he is going to talk about conditions early in accretion history that have some similarities to enstatite chondrites in the sense of being remarkably reduced compared to modern conditions. Is that true, Dave? Yeah. Sure.
So those calcium sulfide and magnesium sulfide, do they occur alone or together with other sulfides?
There's a whole zoo of sulfides in enstatite chondrites. I'll defer to the cosmochemists here, but yeah.
This sample, is it like representing like one type of sulfide or a bunch of sulfides together?
Well, there can be a family of sulfides and they can be isolated. They also link to.
Yeah, I guess still my question is not clear. In this sample, for instance, calcium sulfide, does it exist alone or together with other sulfides?
This is something I downloaded from the web, of course. I was looking for an example of oldamite that was actually kind of somewhat photogenic. So I don't know much about this sample in particular. And Bill and Rick know more about enstatite chondrites than I do.
It's generally interpreted as a metamorphic mineral. So it's probably related either to the planetary metamorphism or maybe the shock. But prior to its formation, there's a whole slew of other sulfides that contain potassium-containing sulfide, magnesium sulfide, all sorts of different sulfides. So basically anything that's stuff in the sulfide.
Yeah, and I should be clear. Most of the magnesium and calcium in an enstatite chondrite are in silicates. But it's after all, it's an enstatite chondrite. But it's so oxygen deficient that some of the lithophile cations are beginning to bond with other things. That's the point. There was something.
The magnesium number?
Yeah.
So high?
Because all of the iron is metal.
Well, it's the silicate portion.
Yeah, the silicate portion. Right. Yeah.
So actually, is this a different situation from the continental lithosphere?
Oh yeah, much more extreme. The continental lithosphere, when it has a high magnesium number, maybe the extreme numbers might be 94, but the average is still, I don't think it's even above 91. So.
You can even add to the fact that there is iron silicide, iron silicon. Silicon behaves as a metal also
Right.
in this meteorite.
Okay, so we're talking about rocks and minerals, but we want to bore down into what they really are. They're made of atoms, so we want to talk about how the atoms arrange themselves in condensed materials, that is to say, chiefly in minerals and to some extent melts, because that's how we're going to come to understand things. And so this sort of brings me into an area that I think everyone has been exposed to in an introductory mineralogy class. And if you don't remember, your memory will be refreshed in this brief tour, right? This is an olivine model. This just happens to be a water ice, but the point is that the point is that there's this geometric arrangement. There's bonding between the different atoms, and this is going to determine the physical properties and the physical and chemical properties of the materials. So obviously there's a, oh, we can play a game, right? What the label is missing. What is that? You can't say, well, Bill, covalent bond, metallic bond, ionic bond, thank you, okay. There has to be some way to make this interesting. It's so obvious. Okay, so we tend to think of ionic bonding as being the principal kind of bonding in major rock-forming minerals, and to a large extent the bonding is ionic, but in fact there's some element of covalent bonding in virtually all of the compounds that we care about. Well, diamond, of course, is made up entirely of a covalent bond, but even things like silica tetrahedra, one really wouldn't want to describe the silicon-oxygen bonds as being purely ionic. There's something in between. And then for the metals, we have this completely different arrangement where the positive cations are charge neutralized by electrons that are delocalized and in a conduction band and free to move around. And in so doing, generate the remarkable properties of metals, the high conductivity and so on. Okay, so when we talk about most compounds, not metals actually, but most compounds in let's say the mantle, we're talking about cation and anion arrangements that we have come to understand following Linus Pauling as being in coordination polyhedra. And coordination polyhedra are a cation surrounded by a certain number of anions. The basic rule is that the cation can't be so small as that it rattles around in the anion cage, and as a consequence, depending on the size of the cation to the anion, one gets different geometric arrangements of the anions around them. And this is governed by the so-called, basically the cation-anion radius ratio, the so-called radius ratio. And depending on the radius ratio, we get different geometric arrangements. So these are the limiting ratios of the cation radius to the anion radius. If it's above a certain number here, 7.73, we have 8-fold coordination, then 6-fold coordination, then 4-fold coordination, and so on. And of course, for silicon and oxygen, that falls very strongly within at least at low pressure, the tetrahedral coordination, and so we end up with tetrahedra. This isn't actually drawn in, but magnesium and iron tend to be, they're not always, but they tend to be in octahedral coordination at low pressure. And the silica tetrahedra, of course, polymerize into various different kinds of arrangements, isolated tetrahedra up to complete frameworks of tetrahedra, as in quartz or feldspars. Why is that there again? Oh, it's because I went backwards. That's why. Okay. And so here's olivine with its isolated tetrahedra. I spent my PhD studying the structure of olivine. I used to think it's chains of oxides is really what it is, but it's isolated silica tetrahedra, and that is something that's governed by this tetrahedral coordination, which is a phenomenon that occurs at low pressure, right? I'm sorry, this is a distorted hexagonal structure.
You have like A2, A4 dialectics. So in this case, you would have the silica tetrahedra pointing up and down.
Mm-hmm.
You would form a hexagonal structure if you already along the right direction for this one. On the side.
Okay.
And then what you would obtain is actually like a hexagonal lattice.
Yeah. I seem to recall that there are in fact high temperature hexagonal equivalents of olivine that.
Yeah, the potassium sulfate and potassium selenate.
Right.
And there is some very weird conditions of very low.
And it's been speculated that these could be stable in actual magnesium, in actual forsterite, but it's never been found. Isn't that right? Yeah. Okay. So this actually is really all I'm going to say about the influence of pressure on this, but these cation-anion radius ratios shouldn't be taken as, out of Shannon and Pruitt as the numbers that apply everywhere, because with pressure the bond lengths change, and therefore really the effective cation-anion radius ratio changes. And so with pressure, one begins to get higher coordination and therefore the stability of different arrangements and the stability of different minerals. And I'm pretty sure that G is going to talk about that in a lot more detail, so I will just leave it at that. Okay, and this just makes the point that when we're talking about silicates on the Earth, we get up to about 135 GPa, and the kind of mineral crystal chemistry that I was just referring to really only applies up here, and there's this whole interesting spectrum of things that occurs through most of the mantle that, again, I will leave to G. Okay, melting, right? Melting is the loss of the regular crystal structure or the regular lattice structure, and we now understand melting of a whole range of materials fairly well. A couple of recent studies determining the peridotite solidus this is the solidus of normal sort of fertile lherzolite, actually, going all the way up to the core mantle boundary, have defined it fairly well. These experiments, you may look at this and you say, well, that's compared to the geotherm in the mid-mantle, that's well over 1,000 kelvins above the mantle melting temperature, or above the mantle temperature, rather, so who cares? But we care for a whole host of reasons, one of which is that, in fact, we do believe that there are melts stable along the geotherm in some relatively interesting places, not near the surface where the melting temperature is low. And that's the role of fluxes that have lowered the melting temperature of peridotite dramatically. And so that's one thing. And then the other thing, which we were sort of talking about just a moment ago, is that in the early Earth, in fact, melting of peridotite is completely relevant. The determination of whether or not you have a whole Earth magma ocean or a magma ocean that's just in the shallow portion of the Earth, or a magma ocean at all, is determined by the thermal state of the Earth as compared to this curve. Notice also that conveniently, the geotherm in what I always used to call the thermal boundary layer, until Dave this morning told me maybe I shouldn't, at the base of the core mantle boundary, just about touches the peridotite solidus within uncertainty of where we know where these two things are. So the speculation that there could be melting today at the core mantle boundary is at least plausible based on the experimental measurements, but of course there's still uncertainty in both of these.
Which study is that?
Let's see. There's two here. This is Andrault et al. And actually, this is it's not actually peridotite. Well, it's aperidotite, but it's not actually mantle peridotite. I think it's an ordinary chondrite. And this is Fiquet et al. And they're both diamond anvil studies starting with glass peridotite.
I mean, it's very difficult to identify whether some of this is.
Yes. Yeah.
What Andrault did was they did in situ X-ray diffraction experiments.
That's right.
While heating, and they looked at the disappearance of calcium peroxide, which they thought was the first phase disappear on melting. And there's some uncertainty there, I think, because the other possibility is that calcium peroxide is dissolving into magnesium peroxide and disappearing.
Yeah, I agree with that. There's a data point that should have been on this diagram and that isn't there, and it's the recent very high pressure shockwave data out of the Caltech lab. I'm trying to remember. I think it's Luo et al. Of melting of olivine. Maybe Sarah knows. Well, no, Mosenfelder. It's actually a reinterpretation of old Aaron's data, but it was published. Yeah. And it actually, if I were to put the data point on it, it's right about there, which is in surprising agreement, which may mean nothing, but. Oh, you mean like an eclogite or something like that? There are no studies, to my knowledge, that are up in this realm. There have been studies of melting. Oh, no, I shouldn't say that. There's the Hiroshi study, but at these pressures and temperatures, and actually also with this kind of amplitude, they're not really that different. I think the uncertainties on the experiments are greater than the differences in the lithology. In fact, that Luo study that I just mentioned is pure olivine, and in fact, I'm willing to make the analogy between that and peridotite, because at these conditions, the real influence, or the real uncertainty is the experimental uncertainty. Rick?
How much of that geotherm is pinned by an assumption about the outer core temperature?
I think this part of the geotherm here, of course, is the adiabat. And this part of the geotherm is based on Lars's assumptions about where he has to go to be at the core mantle, to match a core mantle boundary temperature.
I also said that assumes that the upper and lower mantle is a similar composition.
The geotherm assumes that, or the?
Yeah, from the previous diagram that you had, it sticks through 2009.
Yeah, but the solid geotherm is not going to be very dependent on whether or not the lower mantle is a slightly different composition, right? Again, look at the scale here.
Oh, that's
yeah.
What kind of error bar is there on the temperature at the 660?
Oh, the temperature at the 660 is much, much better, because when we're at the 660, we're in multi-anvil experiments, and I think Dave will be talking about how much we can believe the temperatures and pressures of the different devices. And so I'm not going to, I'll tell you, come to Dave's lecture to hear the specific answer to that question. But it's much smaller than these. It's maybe a couple hundred degrees. At 25 GPa, even multi-anvil experiments have considerable uncertainties because the thermal gradients are really large. But 100 degrees or 200 degrees, I'd say. Oh, I didn't talk about this this one here. I was lazy and I didn't put the geotherm on here, but this is melting of iron sulfur eutectic, so it's melting of iron metal and iron sulfide together, and it's a number of different studies put together, and we don't need to worry about their overall agreement or disagreement. A key thing, though, is if you look here at 50 GPa, melting temperatures of about 1700 Kelvin. That's really cold. Right? If there's metal sulfide present in the lower mantle at fairly high iron activity, then we may have small amounts of molten sulfide through very large portions of the mantle today. Never mind in 4.5 billion years ago. Okay, we're interested in volatiles, of course, and early in Earth history, the volatile inventory in the interior could have been greater if it was delivered by large amounts of carbonaceous chondrite, if volatile people like myself fantasize about large amounts of carbonaceous chondrites because they're just loaded with this stuff. I want to clarify something that, at least from my perspective, that Rick touched on. This is a diagram similar to what Rick showed, where he was talking about volatility of different elements. If you talk to a cosmochemist and you say, what about the volatiles, they'll start talking about things like manganese and copper and so on. Cadmium is a good volatile to a cosmochemist. But from the point of view of material properties, those aren't really the things we're talking about. The volatiles, from our perspective, from the perspective of a mineral physicist, are those that can do a few different things. Right? First of all, they have a tendency to form a vapor phase, and therefore they have a high vapor pressure. And in general, they have a tendency to act as a flux. And in that respect, there really aren't that many volatile species. Certainly the rare gases in nitrogen are always volatile, although they're never present in concentrations large enough to really affect the properties of things much. Hydrogen and water are definitely volatile and certainly the most important ones. Carbon is interesting. We tend to talk of carbon as a volatile, and it is when it's in its oxidized form, but when it's in its reduced form, it doesn't necessarily follow these criteria, right? Carbon in its reduced form as diamond has a very, very low vapor pressure. It's got a very low solubility in any kind of melt or solvent or what have you. And it's not very good as a flux. It doesn't tend to lower the melting points of materials very much at all. So carbon is a volatile, but its ability to act as a volatile depends on its oxidation state. Sulfur has some of these qualities. It certainly has a tendency to form a vapor phase and has a high vapor pressure. It doesn't do a very good job of fluxing silicates anyway, since it's not soluble in silicates to a great extent. And these also have minor roles. So this just demonstrates the point that when components are volatile, they have a huge effect on various physical and chemical properties. So it's well known, of course, that peridotite in the presence of water has this very, very low melting point as compared to an adiabat. So if you have large amounts of water present, this is 26 GPa here, the water lowers the melting point. Remember, the dry solidus was up here someplace. And this is also obviously true of carbon, provided that carbon is in the oxidized form. If carbon is in the reduced form, then this doesn't necessarily apply. Water, or hydrogen anyway, also has dramatic influence on physical properties, and this is what Dave was referring to. I think we have too many Daves here. We're going to have to do something about this. Can I call you just Stevenson? Ruby? What he was referring to is saying you must have water in order to have plate tectonics. The microscopic basis for that is the great power of hydrogen when it substitutes as a trace constituent into mantle silicates to weaken them. Right? And so this is a demonstration of that for a given water pressure or water fugacity and a fixed stress. The strain rate of olivine goes up by orders of magnitude, and so as the strain rate goes up, you could say that the viscosity is going down by orders of magnitude. And this is owing to the role of hydrogen as a trace defect in the structure of, in this case, olivine. So this makes the point that I was referring to earlier. We think that the mantle, at least the modern day mantle, gets more reduced with greater depth. This isn't attributed, but this is a paper from Frost and McCammon, 2008. So based on oxybarometry of xenoliths, as one gets deeper and deeper, conditions get more and more reduced, such that carbonate, like magnesite, is no longer stable, and graphite or diamond becomes stable. So under those conditions, we have different behavior. And this may be actually really important for the behavior of so-called volatiles and their distribution early in Earth history. And there's actually more going on in this diagram than I want to explain. But if we imagine that the carbon is oxidized in the near-surface environment, then we may have a very thick atmosphere with CO2 and so on, and then a lot of CO2 dissolved here. But if the carbon is reduced and certain things are met, not necessarily that they will be, such that diamond actually precipitates in the magma ocean, then that can draw down all the carbon, or a very large portion of the carbon. And instead of carbon being volatile in the sense that it's in the early atmosphere of the planet, it can end up in the interior. Actually, in both cases, the carbon can alloy with core-forming material and be destined for the core, and that's another possibility. So the oxidation state of carbon can have a very significant influence on the distribution of volatiles, and of course we would like some carbon to stay on the surface, otherwise we're going to have a hard time having any beer.
Can you explain what oxidation means and what controls the oxidation state of the planet?
Yeah. Well, no, it depends on our parameter space, how hard or easy that explanation is. But
Simple for now.
Really, when I was looking at the ansitite chondrites, it's as fundamental as that the actual total supply of oxygen is insufficient to oxidize all of the metals, and so you have a large portion of the metals acting as in a metallic form. Not just the iron, but maybe even the silicon, things like calcium and magnesium, unable to find enough oxygen to form oxides and silicates. So that would be very reduced. More oxidized is everything, including the iron. There's plenty of oxygen around, and so you form oxides, and that would be like a carbonaceous chondrite, and that would also be the crust in the mantle of the Earth. The subtleties come in between those areas, where for sure there's most of the silicates, and major rock-forming elements are in oxides or so on, but certain elements like carbon begin to lose the ability to be in an oxidized form. So instead of having carbonate, you have diamond. That's long before you start putting the magnesium and the silicon into reduced phases.
And that depends on the partial pressure of oxygen?
Yes. Well, the word that we like is fugacity, but it's really the same thing as partial pressure, right? And it's the availability of oxygen or the reactivity of oxygen in the system. Okay. I guess we're okay for time. Okay, I've for the most part been talking about that equilibrium world, which I said was a false world. And so I want to talk a little bit about the non-equilibrium world. And there's a series of different micrographs that are peppered through the rest of this talk that are things that experiments that were done in my lab at one point or another that we've never published. And this is one of them. This is a reaction. What was originally over here was an eclogite, and what was originally over here was a peridotite. So this was meant to simulate what happens when a slab sits next to peridotite for 1 billion years. And in fact, this wasn't 1 billion years. This was just 24 hours, because that's kind of our problem, right? We have limited time to get experiments done. We have this remarkable reaction between them. And this reaction is not just diffusion like you might expect. Oh, I said this backwards, didn't I? Obviously, this is calcium, and this must be the eclogite, and this must be the peridotite. The high calcium in the eclogite diffuses down to the low calcium reservoir in the peridotite, but not just diffusion like you would calculate it from an equation, but all sorts of really interesting things, like look at silicon, for example, which actually goes up in the reaction zone because you're making this thick rind of orthopyroxene. And the reason I put this in here is to point out that when we have various assumptions about physical chemistry, textures matter, right? It isn't just one continuum against another continuum. It's the grain size, it's the actual minerals, it's the reactions that are going on in addition to the chemical potential gradients that you might imagine. It's kind of a complex and fun area to be working in. Okay, so we're sort of thinking about some of these things. Not all of them, but some of them. So when we talk about diffusion, normally we may care about diffusion because we're just the problem that I was just sort of indicating. How long does it take before peridotite and subducted crust homogenize one another? Or we may be talking about diffusion across the core mantle boundary. Or we may be using it as in aid of geochronology, or as a chronometer, which is actually what's happening here. This is an orthopyroxene from Mount St. Helens. And in this study, the diffusion profile over here was being used as a test of the time of residence of this crystal in the magma. But when we actually see the diffusion, and this is, I should say, this is a diffusion of iron in this profile. What's actually going on a microscopic scale is a lot more interesting, or potentially a lot more interesting, than you would just calculate from just, say, Fick's law. And that's because in real materials, particularly in real crystals, diffusion is coupled to a whole bunch, or diffusion of elements, is coupled to a whole bunch of structural features in the materials that determine the diffusivity. So in fact, if we had an absolutely perfect lattice, diffusion would be very, very slow. The fact that we have vacancies allow this particular element, or this particular atom rather, to move from one place to another. So the vacancies and the crystal defects are very, very important for pretty much all of the non-equilibrium properties of Earth materials. Maybe that isn't true for melts, but it's very true for minerals. So a really great example of that is what I was talking about before, about the weakness of hydrated olivine. This is actually the results of a first principles calculation that I was involved in, although I didn't do the calculation, trying to locate the hydrogen or hydroxyls in olivine. And what you can see is that these are a number of different configurations. They are all surrounding a tetrahedron in which there is a silicon vacancy, right? The hydroxyls are coupled to vacancies. They may be coupled to tetrahedral vacancies, they may be coupled to octahedral vacancies, but the reason that hydrogen weakens olivine so much is that the hydroxyl simply wouldn't be there if it weren't coupled to the vacancy. And it's in fact the vacancy that allows for greater diffusivity, greater lower viscosity, and so on. So there's a whole zoo of different kinds of vacancies, everything from an actual vacancy to an interstitial substitution to an impurity ion or line defects and so forth. And all of these end up being really important for controlling the transport properties of crystals. the big daddy of imperfections in crystals is actually the grain boundaries, right? One can go from sort of the zero-dimensional or the one-dimensional ones that I just showed you a moment ago, and one can build up two-dimensional dislocations like screw dislocations and so forth. But the biggest kind of defect and weakness in a solid matrix is the grain boundaries themselves. And this too, I left out this attribution. This is Haraga et al. 2004. This is a TEM image of an olivine grain boundary where you can see the lattice fringes of two olivine crystals in different crystallographic orientation. One thing that Taki Hiraga was very interested in was that if one looks at the grain boundary, it's an incredibly narrow feature. This is nanometers here, so the feature is just a couple of nanometers across. But he was pointing out that these features are store of incompatible elements that don't fit in the lattice. So this is concentrations of aluminum, calcium, things like that in the grain boundary are much, much higher than that which are found in the background in the olivine. But in addition to that, I would just point out that this is a high energy feature, right? This is definitely not the minimum energy solution to how the atoms would like to arrange themselves at equilibrium. G? Where this is the grain boundary here.
So when you say the width of the grain boundary is we don't see the width.
Well, it's actually interesting because this is AEM analysis, and it may be that it may be that the AEM analysis doesn't have the spatial resolution to get the grain boundary exactly right. So this may, in fact, if anything, it exaggerates the width of the grain boundary. So this looks to be about 5 nanometers across here, but if I asked Taki Hiraga about this, he'd probably say that the grain boundary is about 2 nanometers.
So how much does this affect the bulk composition of the
Well, Taki's written about that. It's interesting. For anything that has any compatibility in the lattice at all, it's irrelevant. But when you get to the truly incompatible elements, things like cesium and barium and maybe even potassium, at least for olivine, if you sum up the potassium or the barium or the cesium in a peridotite and say how much of it is in the grain boundaries, then you begin perhaps to get not most of it, but tens of percent of the highly incompatible elements. But anything as compatible even as uranium or thorium is still going to chiefly be in the lattice of a peridotite. And the reason for this is that even though the concentrations are small, even though the concentrations are large, the actual volume of a 2 nanometer surface around the minerals, of all the minerals, is vanishing. So it has to, the concentration factor has to be super high for it to matter. Bill?
So when I think about this, the other issue that pops in my mind is grain size from the top to the bottom. That is the relationship of grain boundaries.
Well, yeah, I would say, and maybe this is what you're saying, and I don't quite understand you, Bill, but I would say that as stores of incompatible elements, grain boundaries may not be that important as influence on transport properties, including things like grain boundary migration, grain growth, diffusivity, and so forth. They could be greater.
If we take an element like cesium, it's very low abundance in the mantle. I think about the top of the mantle and the bottom of the mantle, and I think about the proportion of site defects at the top of the mantle indicates that those at the bottom of the mantle. And I can envision the bottom of the mantle being crystal sizes of over a meter.
Oh, I'd like to introduce you to Slava Solomatov. There are people who think the opposite. There are people who think that the grain growth laws in the lower mantle are so sluggish that in fact minerals and mineral grains in the lower mantle are actually much smaller than in the upper mantle.
Okay, the perspective is I'd like to understand where the misfit elements live.
Mm-hmm.
That's all.
Bruce?
Mark, does the structure of the grain boundary depend at all on what gets stored there, or are these sort of
Depend at all on?
What gets stored there? Are these incompatible?
Oh, that's a good question. David Kolstedt and I think also Uli Fowle and a number of other people have been working on doping fairly clean systems like pure forsterite with different amounts of trace elements and then measuring physical properties. In Kolstedt's case, of course, he's measuring creep properties. And I don't know the answer to that. I think it's an interesting question. Does it depend on the concentration and the type of element that's sitting there on the grain boundary? One thing that I will gloss over very quickly in a few moments is that the people who are studying rheology increasingly think that grain boundary sliding, that the grain boundaries themselves is a really important component to the constitutive laws of mantle flow. And if that's the case, then yeah, you begin to care about grain boundary chemistry a lot.
To follow up on Bill's comment, if the magma ocean led to small crystal size relative to what you eventually wanted, then this is a way of storing a lot of elements that you would normally think of as incompatible in the solid phase, right? Initially.
Initially, perhaps, but I guess that
eventually the question comes: how do you leach them out?
Yeah, or how do they anneal out? That's right. Someone, Rick.
That was my point. I mean, when you look at like mantle xenoliths, and you make mineral separates from them, you know that when you subject those minerals to weak acid leaching, you remove most of the incompatible.
Right.
You know that this stuff is sitting right on the surface of it. But what you don't know from the natural example is whether it was really there in the mantle. One of the things that happens with peridotite is they're brought up as a xenolith as all the minerals expand, and the grain boundaries open up basically. So it's not impossible that what's on the grain boundary was injected by the process that brought it to the surface. So it's a bad experiment, but it's known for a very long time that most of the incompatible elements in a mantle peridotite are sitting on grain boundary.
Now, one thing that I should point out about this, I'm glad you guys are interested in this, actually. This is olivine. This is aluminum, calcium, and nickel, titanium, and so on, right? And this is a grain boundary. It's an olivine grain boundary. It's not a clinopyroxene olivine interphase boundary. It's not a garnet clinopyroxene boundary. It's the simplest possible grain boundary, at least that we have in peridotite. And so, what may be occurring in terms of the concentrations of other elements in more complex boundaries, this doesn't address.
But this would also mean that if we calculate or measure partitioning coefficients, we would get to misleading because all these incompatible elements will go on the boundary, so we would measure or calculate in the bulk sample.
Yes, but what I said before is because the total volume of grain boundaries, at least in a rock that has 100 micron size grains. If we're talking about a rock that has micron size grains, I take it back. But for a rock that has any kind of quasi-macroscopic grains, the total volume of grain boundaries in the rock is so small that even very incompatible elements are still dominated by what's stored in the lattice, except for the most extremely incompatible ones. Dave?
Were such elements on the grain boundaries in the boundaries?
Oh yes, I'm going to show you an example of that, and it doesn't even have to be. It doesn't even have to be this, but this definitely matters, right? If we want the grain boundary to migrate, right, it can migrate only as fast as the incompatible elements that are sitting on it are able to move. So yes, incompatible elements can definitely make grain boundary migration sluggish, and that's why people like Kolstedt and Fowle are interested in the relationship between grain boundary poisoning, if you will, and transport properties. Colin?
If you wet the grain boundary, would this effect go away?
If you wet the grain boundaries.
Yeah, if you're undergoing partial melting, would this grain boundary actually partition between a solid and liquid?
Yeah, we should be careful. I didn't include a lot about melt textures, and in fact, I didn't include anything about melt textures. But in general, small amounts of melt aren't on grain boundaries. They're in three-phase junctions, right? They're in the triple junctions. But nonetheless, the moment you have a phase that likes these elements, it depletes not just the lattice, but also any of the other components with, or I don't know if I should call it a component or a species or a phase. Let's call it a phase. A grain boundary phase will not successfully compete for these elements compared to a melt. Okay. So grain boundaries are kind of high energy environments, and the system wants to get rid of them, right? And that's the motivating force behind grain growth. As as a rock sits and the total surface area of the grain boundaries is reduced, the free energy of the system is reduced, and the consequence is that grains grow. So that's just a simulation illustrating that with no particular physics behind it. And so you might think, well, that's great. We should end up with really large grains. And Bill just suggested perhaps that we could have meter-sized grains in the lower mantle. If we take this to its extreme, and actually this was motivated by something else, we may think the inner core. Grain growth in metals is incredibly fast, and the inner core is really hot, and so. Actually, this article was not motivated by that. But how come grains aren't really huge in the mantle if the system wants to get rid of grain boundaries and grain growth is so favored? Two reasons. One is that grain growth really isn't as simple as you might think it is when you talk about a rock as compared to, say, an aggregate of a pure phase like olivine. So this is yet another unpublished experiment. What we did is we put in micron-sized, I think 3 micron-sized, olivine powder into a high-pressure apparatus, and then over that we put olivine and orthopyroxene of the same grain size. So this all started out as 3 micron grains. Held it there for 24 hours, 1200 degrees, which isn't that hot. And at the end of the experiment, the olivine and the orthopyroxene remained about 10 microns, and the olivines, I don't know the exact size, but there's a 200 micron scale bar. They're gigantic, right? The grain boundaries and an olivine-olivine aggregate migrate very, very fast. They just have to exchange isochemically with one another, and so you get incredible grain growth in a monophase aggregate. And maybe this does apply to the inner core, but it certainly isn't what the mantle is made of. Whereas a real rock, in order to affect grain growth, you have to actually diffuse composition. For olivine and orthopyroxene, you have to move silicon around in order for one grain to grow at the expense of another. And as a consequence, the properties of the properties of grain growth and associated things with grain boundary migration are very much controlled by the texture of the material, the fact that it's a rock as opposed to a monomineralic aggregate.
Even a monomineralic aggregate can that cause, because grain growth laws, the rate of grain growth decreases exponentially in size.
Oh yeah, but actually, this is really fast. I haven't done the calculation of what sort of grain growth that you would end up with. This is 200 microns in 24 hours, and it's not even that hot. If you give me 1 billion years, I'll make really big crystals out of this material. I wouldn't be surprised if you'd make meter-sized crystals.
It wouldn't be the size of the inner core.
No. I'm not making that argument. I'm just.
But they are pretty big. It's square root of time or cube root of time.
Mm-hmm.
It's at low pressure.
This is at low pressure, but I don't think that the grain growth laws have a very strong pressure dependence. And in fact, grain growth I'm not seriously suggesting that the inner core is made of a single crystal, but if there's any place on Earth where grain growth is really should be thought about, it's the inner core. Now, there are stresses in the inner core that probably have grain growth reduction or grain size reduction as well, so it's not quite so simple. But anyway.
But Mark, this diffusion depends on vacancies. So wouldn't you expect vacancy numbers to be pressure then?
No, this kind of grain growth doesn't depend on vacancies in the crystal. The grain boundaries themselves are the fast paths, right? It's the things that are being eliminated by the grain growth. So no, it doesn't require intracrystalline vacancies. How do what? Oh, because if this is an olivine lattice, right, and this is an olivine lattice with a different orientation, we just need the monolayer over here to attach across the boundary with a different orientation. There's no need for it to overcome any potential barrier and diffuse across a lattice like it would be for diffusion, volume diffusion in a crystal.
Just the local variation.
Yeah.
Minimization of surface energy.
Yeah.
Yeah, it's driven by surface area.
Okay. Okay, so what I was saying is how come you don't end up with really large crystals? And again, I don't really, the idea of a single crystal in the inner core is not really what was motivating this, but I just wanted to make sure that at least a few people were awake at the end of my talk. Recrystallization of rocks in general occurs in response to deformation, right? So we have grain growth making the crystals larger, but deformation makes crystals smaller. And in fact, it's the balance between those that are going to give us the grain size distribution that we'll see in any given domain in the Earth. Now, peridotic myelinite is an example where this has kind of run away, and micron-sized crystals have been made. And yeah, I'm almost done. So I just want to talk a little bit about deformation and creep in the mantle. There are different modes of creep that depend on things like the stresses and the grain size and so forth. So this is a plot of olivine deformed at modest pressures in the presence of water. So this is really the weak stuff, as it were. The relationship between stress and strain. At low stress, there's this linear relationship, and that is thought to be diffusion creep, and I'll show you what diffusion creep is in a moment. And then at higher stresses, there's a change in the law. You get much, much higher strains for a given increase in stress, and this is thought to be dislocation creep. So one can map out where one gets dislocation creep and where one gets diffusion creep as a function of the stress and also the grain size. And I mentioned, but I don't really have much supporting it, there's this third deformation mechanism which is increasingly important, or thought to be increasingly important, called grain boundary sliding, where it's actually the grains moving along the grain boundaries that is thought to be the principal deformation mechanism. But let's just focus on diffusion creep and dislocation creep. So in diffusion creep, the grains are small enough so that you don't actually have to recrystallize the grains in order to accommodate change in shapes of the crystals because of an applied stress. But diffusion, either through the crystal or along the grain boundaries, is efficient enough to reshape the crystals in response to the deformation. But dislocation creep are crystals that are too large or the stresses are too great to allow diffusion to be active. And then one starts activating sort of large-scale 2- and 3-dimensional dislocation trains through the crystals. This is really cool. I found this in the literature. This is halite that's been deformed and then irradiated, and then the irradiation highlights the dislocations, which are this. So these are individual halite grains deformed in diffusion creep. In dislocation creep, and then the light things are the dislocations. And what you can see is that the dislocations are in fact sort of junior grain boundaries, and in fact a term for these is that they're becoming subgrain boundaries. And when enough rotation and deformation takes place on them, then they actually convert to grain boundaries. And as a consequence, during dislocation creep, the grain size is, if not reduced, at least maintained, because grain growth competes with the fact that grains are breaking up along these dislocation trains. Okay, so this is just this is my last slide. I made this point rather forcefully, but I could have made it with this really simple diagram. One thing that one must be careful about as a consumer of mineral physics or earth materials literature is to remember that what we really care about ultimately is rocks. And in many cases, it's much easier, whether it be with theory or with a diamond anvil experiment or any kind of experiment that you may be reading about, to work with a single phase and to determine the properties of a single phase of a particular mineral, olivine, and so forth. In fact, a great deal of the complexity of earth materials is that the phases work in concert. We all know that the melting temperature, except for maybe at the core mantle boundary, the melting temperature of a pure mineral isn't really that interesting when it's sitting next to another mineral. The eutectic temperature is completely different from the melting temperature of the individual minerals. Similarly, in this case, grain growth of olivine is not really a relevant kind of process for understanding the maturation or deformation or anything in the mantle. One has to take into account that the rock has intrinsic different properties from the constitutive minerals. Okay, and I'm done.
any idea how big the grain started when the mantle moved from the
I will let Dave answer that question, actually. I think that it's a really tough problem.
Yes, it is indeed. I mean, I started working on that with Slava Solomatov. He's still working on it. That's after 20 years. There are ideas about what determines the grain size in the magma ocean that has to do with how quickly the ocean mixes. But then when it comes to the percolation regime, I think there's a lot of uncertainty. It will certainly be affected by small amounts of water, for example. So I don't think we know.
Yeah, just to add to that complexity, one thing that I would really like to know is when the magma ocean crystallizes, how efficient is the separation of minerals from melt?
Yeah.
Right? How much of the melt that is residual in the interstices in the last few percent escapes out and mixes back with the magma ocean, and how much remains trapped in the solid? That has everything to do with the volatile inventory of the interior of the Earth, for example, as well as trace element distributions, trace element concentrations, and so on. And I've never seen anybody address it. I do know, if any of you have any backgrounds as geologists, right? If you look at very large layered mafic intrusions, they seem to be incredibly efficient at expelling the residual liquid. Whether or not the magma ocean crystallization was anything like that, I think is a really great question. Go to it.
Your colleague, Dave Kolstad, might have a partial answer to that, because when you deform the partial melt, there is a tendency for the melt to concentrate, and that enables it to get out quickly.
Gee.
So I have a comment about what stops grain from getting very big. So I remember there's also another effect about when you have perovskite formation. You have the olivine composition going from ringwoodite and then decomposing to perovskite and ferropericlase. There's a grain size reduction effect. And if you have abduction in the plume rising or crossing the transition zone, then there is a strong effect of reducing grain size. So that's in addition to the thinning and the deformation.
Because your voice isn't very loud, I'm going to do what I'm supposed to do after every experiment and repeat what you just said, because it's very interesting and I think everybody should hear it. Right? When material crosses the 660-kilometer discontinuity, and in particular when it crosses on the way down, meaning it goes from olivine stoichiometry minerals like ringwoodite to perovskite and ferropericlase, that reaction is associated with beginning of growth of perovskite grains, and those initial grains that form are tiny. We know this from experiment. And so we get grain size reduction. And grain size reduction is associated with all kinds of changes in physical properties. And I think it's a really interesting point. And I said this in response to something that Bill said. Slava Solomatov has suggested that the net result is, basically a myelinitic lower mantle. That the lower mantle is so fine grained that it, micron-sized grains. That might be too extreme, but it's definitely something to think about. Matt?
So the slabs are really fine grained. Shouldn't that affect their seismic properties in a predictable way?
I like that I can let someone else answer these questions. The influence of grain size on seismic velocities. Oh, we're back in the inner core. Yeah.
There is attenuation.
Yes, there's more attenuation on one side than the other.
Right, it will correspond to crystals like the other side.
So again, I'm going to repeat that. This is an observation of asymmetric attenuation in the inner core that's been attributed to dramatic differences in grain size.
But it could also be
Either or.
I guess if the former lithosphere that's going down has remnant anisotropy,
Mm-hmm.
when you transform to perovskite and you sort of restamp that such that you don't have anything, the strain building up to a line stuff.
Right. You could lose the anisotropy?
You lose the anisotropy, and you have wave path systematics that are actually affected by that and map into tomographic models. That could be there. But to argue against that, one might say, well, the tomography that shows the blues going through the 660, the blues don't suddenly disappear. So
Mhm.
maybe not.
But that might relate to just what Barbara said, is it's still cold.
Yeah.
But some blues, actually, most blues disappear.
For those who don't know, when the coffee at 3:30 is accompanied by cookies, right? Usually. but I think we have to wait another 10 minutes before the cookies are available. But we can wrap up if there are no further questions.
I have a very naive question. How does the core-mantle boundary end up at the radius that it ends up at? It's a matter of how much iron there is? Or
Yeah, it's the proportion of iron and silicate that was delivered to the Earth. The thing that I think is amazing, of course, is that just happens to be a depth and pressure that is so close to that phase transition to post-perovskite.
No.
Well, it may not be. No, wait a minute. It may not be at that depth, but it's undeniably close.
No. No. The amount of metallic core we have is a function of how much oxygen we could have had. We could have had no metallic oxygen, unmetallic iron.
Well, okay.
C1 chondrite has no metallic iron. So you just have to have an abundance of oxygen. That's it.
No, you said that backwards. We have a certain amount of oxygen as compared to metal, and so we ended up with that much metal and a certain amount of silicate. Right. So yes, you can call it the abundance of oxygen, or you can call it the abundance of native metal. It's the same thing.
No, if you have native metal, you throw more oxygen at it, you get rust and use that.
No, but it's cosmochemically determined. On that we agree.
I'll talk about that a bit next week, I guess.
Okay.
In the context of exoplanets, people have suggested cases where planets the size of Earth would have no metallic core. Of course, FeO can become metallic at low pressure, but it wouldn't be a metallic iron core.
Iron oxide. And the moon is an example of a planet that almost doesn't have a core, right? It's in terms of mass significant. Okay. Coffee and cookies soon, right? So after coffee, we return to talk about what we're doing here this month.